So we are at the end of the second module of this course. Second module. So the third module will start. The interstellar medium. No, it started with clusters and AGN and all that. Part of the second module. So today we'll be talking about high redshift galaxies. Okay. So about a month we'll have for ISM after today. Okay, so let's get back to where we were last time. So we were talking about these high redshift quasars and how their spectra or their SEDs have a lot of information about the intervening intergalactic medium. We talked about characteristic SED spectrum. It has a very broad peak in its Lyman alpha, in its own rest frame, and that broad continuum is affected by the intervening medium. So this is a quasar. These are a bunch of quasars at different redshifts, and what you see is that on the blue side of the Lyman alpha peak of the quasar, as you go to higher and higher redshifts, the absorption becomes more and more, right? You can actually see a distinct evolution in the Lyman alpha. So these sort of features on the blue side of the bump, the Lyman alpha bump of the quasar is called the Lyman alpha forest. So basically the forest of these lines, these are lines due to intervening clouds of neutral gas, which absorbs at their respective Lyman alpha transitions, right? So, so for example, this absorption feature is due to Lyman alpha, which is near to us compared to say this one, okay? Because it's more blue compared to this one. The other thing is you can actually see in the background continuum, there's also a little peak here. This is the Lyman beta peak in the quasar spectrum itself. So beyond this Lyman beta, there will be absorption, Lyman beta absorption due to neutral hydrogen in the intervening medium. So, this quasar absorption spectra carries a lot of information about the history of neutrals in the intergalactic medium, reionization, and so on. And this Lyman alpha transition is a very strong transition. And that's reflected here in this expression for optical depth. In fact, even a column which is as small as 10 to the 17 particles per centimeter square, 10 to the 17 neutral hydrogens per centimeter squared is enough to significantly absorb the background continuum. So 10 to the 17 column is actually quite small, much smaller than the interstellar medium column, right? So, so interstellar medium density is 0.1, and it's say 100 parsec. So 0.1 times 100 parsec is 3 times 10 to the 17 already. So even that is enough to absorb, more than enough to really nicely absorb all the background continuum. And there's a whole phenomenology depending on the column density of the absorbing gas. There are systems which are called the Lyman alpha forest, for example. These, if they are deeper, then they are called Lyman limit systems. So if the column is greater than 10 to the 19, the central part, for example, here, the central part of the line is totally absorbed. But then there are also absorbers like, let's see, this one, which are very broad, and you can actually see some light coming in the wings of the of this absorption line. So these are called DLAs, or damped Lyman alpha systems. So they have column densities greater than some few times 10 to the 20 particles per cc. So there's a whole, like, understanding of all this. This is other expression that, if you write this optical depth as a function of baryon fraction and redshift omega matter, what you can immediately see is that the fact that it is not totally absorbed, because this is a tau of 10 to the 5. If xh1, if the neutral hydrogen fraction was order unity, you should see nothing here, right? So the fact that you see a lot of light being transmitted means that the xh1 is small. The neutral fraction of the IgM at these redshifts is small. So after doing modeling of such quasar absorption lines, one can actually calculate the evolution of neutral fraction as a function of redshift. So these are data. So you notice the scales here. So this is a log scale, and this is a linear scale. So till redshift 6, by modeling these Lyman alpha, forest, and other absorption features, you infer that the ionization fraction is very high. Basically, neutral fraction is very low. Most of this IgM is highly ionized, and neutral fraction is only 10 to the minus 4. As you cross this redshift of 6, you see that the forest vanishes, and you are getting more and more totally absorbed, and that sort of indicates a rise in this neutral fraction. Yeah, so this is redshift. This is a quasar at redshift 6.29. I mean, this is the quasar spectrum. So you have the background continuum. If there were no IgM, it would look like this, except it's totally absorbed. Basically, all of this has been absorbed. The lines have become so deep and pervasive that nothing gets transmitted, essentially. This is the Lyman, this is the Gunn-Peterson trough. Essentially, this would become 0 if you go even higher redshift. So using these kind of data, you can actually constrain the ionization fraction as a function of redshift. So these are some of these data. These are upper limits, so they're not that useful. But these are detections and lower limits. So the neutral fraction has to be here or slightly higher than here. And the shaded region is sort of the allowed evolution of the neutral fraction of the universe from different data. So these data, I think, are from some other probes. This is based on quasars, but quasars are not very good if you go very high redshift, because everything gets absorbed. This, even for a neutral fraction of 10 to the minus 2, everything gets absorbed because it's a very strong transition. So this is from other kind of probes. So there is a CMB polarization as well, which gives you an independent probe of the ionization history of the universe, right? So the CMB is a black body, but there is all this intervening electrons, and the fluctuations in the density of these intervening electrons causes the CMB to get polarized. If there was no intervening medium, it would be perfectly black body, hence unpolarized. But because of density fluctuations in the universe, and hence fluctuations in electron number densities, there is a slight polarization that's induced in the CMB, and that polarization is caused by electrons. So if the universe was reionized, say by redshift 20, right? So you will be gathering this polarization signal from redshift of 20 till now. Then the polarization would be high. If the universe reionized at redshift of 6, the polarization strength will be lower because the column of electrons that have polarized the CMB is smaller. So by measuring the polarization of the CMB, you can put constraints on integrated column density of electrons. Okay, so that's an independent measurement on the ionization history of the universe, and they're somewhat independent, right? This you cannot probe really beyond 6, 7. That is an integrated effect from redshift of 1,100 till now, and that's not as sensitive. I mean, that's just doing the electrons, and that's not as sensitive to even a slight neutral fraction. So it requires a substantial neutral fraction in order to build that up. So this is sort of the reionization history scenario that people have constructed using these kind of measurements. Yes. This one. Oh, this is the quasar continuum itself. The quasar has a peak at its own rest frame Lyman alpha, which is 1216 angstrom in its own rest frame. So now if you put it at a redshift of 6.29, 1216 times 7.29 is that peak. Everything on the blue side of this will encounter neutral hydrogen, and it will just get absorbed. Right? So as you go to higher and higher redshift, the fraction of neutral IgM increases. This peak is just the inherent peak, continuum peak of the quasar. No. See, neutral hydrogen can only absorb at wavelengths shorter than their Lyman alpha transition, right? If you have hydrogen in the ground state, it will not get excited from n equal to 1 unless it gets an energy which is equal to the energy corresponding to n equal to 1 to n equal to 2, right? That's the Lyman alpha transition. So these photons in the these will be redshifted. So you have neutral hydrogen here at this redshift. These photons will get redshifted for those absorbers, and they are essential for them. The neutral hydrogen is essentially transparent. So this is totally transmitted because these photons don't have enough energy to excite the electron in the ground state of hydrogen to the first excited state. Okay, good. That's why this portion, the red part of this quasar SED does not get affected. It's only the blue part which has enough energy to excite transitions in the intervening hydrogen that does this. Okay. Now, so this is sort of again another example of this is over a redshift of up to 8. Now these are some sort of theoretical models, and this goes up to the CMB redshift. What is shown on the left is the neutral fraction at the mean density, basically the average neutral fraction in the universe. Okay, and I told that in this Lyman alpha forest, the neutral fraction is 10 to the minus 5. Okay, so this is from these quasar absorption line studies. Then the CMB electron scattering optical depth tells you that reionization sort of happens around redshift of 10. So this is that. This is from the CMB. Now this is where you get this redshifted 21 centimeter signal. So this is like the state of the art in observational cosmology now. That what happens to the universe between redshift of 10 to 100, and the 21 centimeter transition can actually tell us a lot about the IgM history in those redshifts. Now this is of course the CMB, right? The neutral fraction. So these are the dark ages, right? These are the dark ages when the first stars were just sort of forming, but most of the IgM was all neutral. Of course, before the CMB, it was again ionized. So this is sort of a nice thing to keep in mind. Now, on the right, again, these are theoretical curves are theoretical, but these data points are actual inferences from data. So this is very high redshift. This is the CMB epoch. The dashed line here is the temperature of the CMB. The CMB temperature goes like 1 plus Z, right? Because that's the wavelength. The temperature is inverse of the wavelength. So the wavelength just gets stretched with time. So this goes like 1 plus Z. Yeah, that's what we are seeing. The CMB is light which is coming from a redshift of 1100. The temperature, the actual temperature of that CMB is around 5000 Kelvin. That's when the electrons and protons recombine and become neutral.
So what we see CMB, that is redshift 1000.
Yes, the surface of last scattering, which is the CMB, is redshift of 1100.
As we go closer, so when we go from redshift of 1000 to redshift of 1,
Yes.
to see this whatever, for example, the redshift at 21 centimeter signal, does it become easy or it becomes difficult? Like if I want to see redshift 21 centimeter signal,
It's very difficult, right? Because
I thought seeing like going the other way would be difficult. How is it? Going from 1 to 1000 is difficult, or 1000 to 1 is difficult?
it really depends on what you are trying to see. So things like there are these HERA and all these experiments are trying to do this. Even this global 21 centimeter edges and all this was trying to do this. Okay. So it's very difficult, of course. Yes.
But CMB we can easily get.
Yes. Because the CMB is very bright. It's this black body. If you look at the broadband SED of the sky, the CMB is like extremely high peak. The energy density in the CMB is the highest of all the radiation in the universe. So it's a very, very bright source of light. Okay. This is a very faint thing, To dig out 21 centimeter, you have to remove the galactic synchrotron and dust emission, and it's actually an extremely difficult task.
CMB is even brighter than the galactic force.
Yes, at that waveband. You remember I had shown this broadband SED, and at millimeter CMB is really like very high peak. So at hundreds of gigahertz, CMB is what you will observe. If your eyes were sensitive to that waveband, the whole sky you would just see the CMB, and you don't have to subtract anything. That's why in the original discovery of the CMB was these horn antenna. You point it to any direction and you are getting the static in all directions. It's not like you had to subtract something out to get this signal. Okay. So this is how the temperature of the universe on average evolves as a function of redshift. Right, so this is like few thousand Kelvin, as I said. This is the temperature below which hydrogen recombines. Electrons and protons recombine to form neutral hydrogen, and that's why the CMB photons are just, freely streaming. Before that, there are electrons, and the electrons are sort of, provide this higher scattering cross section. So the photons before the CMB era are doing a random walk. But as soon as the hydrogen recombines, it becomes a transparent medium. This is what happens here. And then, so this is how the CMB temperature evolves. This is just 1 plus Z. This is how the gas temperature evolves, is expected to evolve. The gas is initially coupled to the CMB by inverse Compton scattering. The electrons in the gas and the CMB photons are sort of exchanging energy. But at some point they stop exchanging energy, and the gas becomes cooler than the CMB. And then so this is how the gas temperature evolution looks like. And once the universe gets reionized, the gas again becomes heated up by by stellar radiation, and reaches this 10 to the 4 Kelvin. So I was actually trying to recall why this temperature is lower. Right. So gas is non-relativistic component. So P over rho to the gamma is sort of an adiabatically expanding system as a whole. So so P is proportional to rho to the gamma. Rho goes like 1 plus Z to the minus 3. So this goes as a steeper power of redshift compared to the CMB temperature. So it sort of is cooler, is expected to be cooler compared to the CMB. Okay. And then once the first stars go off, the gas gets heated up because of radiation. And this is that neutral hydrogen Lyman alpha forest and all that. Beyond a redshift of 2, within the so Z less than 2 is when the these neutral IgM traced by Lyman alpha actually gets further heated up due to structure formation. And the gas sort of bifurcates. Some of it is still at 10 to the 4 Kelvin. And some of it goes into something called the warm hot intergalactic medium, or the WIM. That WIM is like an X-ray emitting gas, but it's extremely diffuse. So you can, I mean, it's almost impossible to observe WIM because it's very dilute and it emits in X-rays, but the emissivity is very low. But it contains majority of baryons in the nearby universe. So this is, this is another frontier of the present day galaxy formation and extragalactic astronomy. Okay. So as I mentioned, yes. Right. So right. So here maybe I can show you the reason behind that bifurcation. What happens is that at high redshift, the structure is still forming, and the low density IgM still is not very, very dense. At lower redshifts, the structures become more nonlinear, and the IgM gets heated because of gravitational collapse. Even though those structures haven't virialized in form of halos, they have become deeper potential wells, and being in deeper potential wells, they get heated up. These are just structure formation shocks and weak shocks which heat up the gas above this Lyman alpha temperature, which is around 10 to the 4. Okay, so as I mentioned, this quasar spectra carry a lot of information. Here is an example of something called the quasar proximity effect. So if you look at this quasar, okay, what quasars do is they produce a lot of ionizing radiation, okay, and they ionize a region around them, sort of shown schematically by this sphere. Okay, so all this is ionized, and this can be hundreds of megaparsec. If the quasar is very bright, it can ionize a reasonably big region around it. So if you look at the spectrum of this quasar, you don't expect a lot of absorption here because all this gas is fully ionized, right? Only beyond this, only at redshifts smaller than this, you will start to see absorption. So you can actually see this is the quasar continuum, but in this wavelength window, there is no absorption. This is because of this quasar proximity effect. The gas in the proximity of the quasar is fully ionized, so that's why it does not show any absorption. Similarly, if you have a foreground quasar along the sight line, you can have this region which is devoid of any Lyman alpha forest. That's because this foreground quasar has ionized this region. So in this redshift range, you don't see absorption due to neutral hydrogen. So this is the transverse proximity effect, and this is the line of sight, or the line of sight proximity effect, because this is due to the ionization bubble along the line of sight. This is due to ionization bubble in the foreground due to other quasar in the transverse direction. So, I mean, these things are used, as I said, this carries a lot of information. You can actually do some sort of a tomography that in this region, there is an AGN right here, and it ionizes this much region around it and all that. So you get a sense of 3D distribution of ionized regions in the IgM. This spectrum is from this quasar. You're not seeing the light from that one. You're just looking at the light from this one, right? Yeah. Yes. So if you look directly at this quasar, then of course you will see, I mean, you will not see absorption here as well.
You see something like this feature?
Yes, yes, you will see something like this. So you will have this, and then you'll have the Lyman alpha peak of this quasar. It's actually extremely simple, but very, very strong. So these ionization spheres are analogous to something called Stromgren spheres around O and B stars. So these massive stars, which we will actually deal with in the ISM part, produce a lot of ionizing photons with energy greater than 13.6 eV. So they just photoionize the gas around it, and it forms this sphere. I mean, if the ambient medium is uniform, it forms a sphere within which there is a balance between ionization, photoionization, and recombination. So within that radius, uh, the gas is almost fully ionized. Outside it, it's fully neutral. So this is called the Stromgren sphere. So this is another schematic representation of the same thing. So if you had a very, very high redshift quasar, something like this is the Lyman alpha peak of the quasar. It's all absorbed, right? You know, this is totally absorbed. This is like the Gunn-Peterson trough because there's nothing here. Then you have these first stars which start ionizing the portions of the IgM, and say here, uh, this is now this portion is ionized, so that's why you can see some flux here, which is able to leak. Again, this part is ionized, so you can actually see some flux coming from here. And you know, here essentially it becomes very transparent, and only little pockets of neutral hydrogen, which gives rise to Lyman alpha forest. So this is sort of showing the ionization history of the universe in a schematic. It's very difficult to do such a broad range of wavelengths in reality, and very difficult to find quasars at very high redshifts. Okay. These Stromgren spheres are also called H2 regions. H2 meaning hydrogen is fully ionized, H plus. Right. So when the H2 regions start to overlap, normal Lyman alpha forest starts to become. So there are only like little clouds in between these ionized bubbles where you'll have absorption. Okay. So I mean, it will be good to have some sort of a census of baryons in the universe. Where are most of the baryons in the universe? And we already know from cosmology that only 5% of the mass energy in the universe is in form of baryons, in form of ordinary matter. And out of this ordinary matter, this is roughly how, at redshift of 0, uh, it is distributed. And I told you about this warm hot intergalactic medium, or the WIM. You see this guy? This is this WIM, which is extremely difficult to observe. But it is the most dominant component of the baryons in the universe. Most of the baryons in the local universe are in this warm hot intergalactic medium. These percentages are like rough. You know, you don't trust them to, like, you know, the last significant figure which is shown here. Now, if you go to higher redshift, the WIM becomes smaller and the Lyman alpha forest becomes the bigger portion of the total baryons. And in fact, there are two parts of the WIM, the hot WIM and the warm WIM. So, you know, they're all has a lot of mass, but very difficult to observe. This is the ISM and the stars that, you know, we're mostly studying. So stuff that we can actually easily see is extremely tiny, even out of this small fraction of the whole universe. So basically, there's a lot that we don't understand. Of course, in the exotic stuff also, but even in the ordinary stuff, which is governed by the standard model of particle physics and whatnot, we really don't know most of the normal baryons are. Very difficult to find them observationally. So IgM, which has all this, is the biggest reservoir of baryons in the universe, and not the galaxies, and not the galaxies' halos, not the clusters. They're all very bright, but they don't have most of the baryons in the universe. Okay. galaxies are clustered. That is, if you have a galaxy in some region, the probability of finding a galaxy within its neighborhood is higher compared to probability of finding a galaxy in a random region. So galaxies appear clustered. And the reason for that is sort of qualitatively shown here. So this dash line shows the large scale matter density distribution. So there is a large scale or low K density distribution mode, and on top of that there is a high K fluctuation. And this horizontal line here shows that if the density crosses this threshold, galaxy will condense, and the halo will condense and form stars and form a galaxy. So what you can actually see is that all these peaks which are closer together will form galaxies. So this is like a rough picture of why galaxies are clustered together.
Spatially clustered, or you are seeing a galaxy nearby, how far that galaxy is
Clustered both in the sense of clustered on the sky and also clustered in 3D. Yes, in 3D also they are clustered. Right, you see galaxy clusters, they're so rich in galaxies. Megaparsecs. Kiloparsec is the size of an individual galaxy. Okay, and the other thing that you should really be familiar with is something called the bias parameter. So bias parameter, so this, to quantitatively describe galaxy clustering, people use something called 2-point correlation function. So that 2-point correlation function quantifies the probability of existence of, so given a random direction, what's the probability of finding a cluster? Given a direction which is offset from the location of a galaxy by this much, what's the probability of finding a cluster? So that excess probability of finding a galaxy is quantified by this 2-point correlation function. It sort of quantifies how correlated the location of galaxies are. Okay, and this xi here is this 2-point correlation function. And from observations, we measure the clustering of galaxies. But theoretically, a lot of times we are interested in how clustered the matter distribution is. And the matter is dominated by dark matter, So there is something called bias parameter, which tells you how the visible galaxies, how much biased is their uh, occurrence compared to the actual mass distribution of the universe. This is called the bias parameter. You don't have to know it quantitatively, but you should know this term. The bias parameter is a way to go from galaxy observations to mass distribution. Yeah, those ideas apply. Those ideas apply in galaxy clusters as well. There is tidal stripping of galaxies and all whatnot. So galaxies are clustered together, and dark matter and galaxies are not perfectly coincident. These are the two ideas in this slide. Now, why do galaxies have disks? Why do galaxies have components which are rotating? Where do these galaxies gain this angular momentum from? And answer to that is gravitational tidal torques. Okay, so for example, so if you have this initial density field, like linear small density field, if your surrounding density field has a quadrupole moment, right? You can actually expand any field in terms of its monopole, dipole, quadrupole, and octopole, and so on. Quadrupole and higher multipoles can give rise to tidal torques. Okay, and it is sort of diagrammatically shown here. So this is all happening in very early universe. even from the CMB epoch, you integrate it out and see how much rotation does it impart. So this is a excess of mass here, okay, and this is some sort of a proto-galaxy. Now this excess of mass just pulls this side. It does not give this proto-galaxy a sense of rotation, right? It's just pulling it. Now consider a dipole, plus minus, excess of mass and a deficit of mass. There is an extra pull on this side, and this is just pushing it back. So again, it is just sort of pulling this mass distribution. But if you have a quadrupole, which is shown here, right? Quadrupole is shown here. This is pulling, this is pushing, and this is pushing. So this lump of matter gets rotation, right? Here you don't. This lump of matter does not gain rotation. Even here it does not gain rotation. But if you have a quadrupole mass distribution, you have a net pull in this direction. Here there is a net pull in the opposite direction. So there is a sense of rotation that's imparted to this proto-galaxy. So this is what is thought to impart rotation to galaxy halos, to the halos. Okay. So plus minus is the excess of mass. So delta rho being positive, delta rho being negative. That's plus and minus. So that's why this is a monopole. This is sort of a dipole. You have excess of mass here and deficit of mass here. It just sort of pulls. Whereas here you can actually see that there is a rotation. So if you do it quantitatively with all this delta, if you do cosmology, there is this delta field over density. And if you expand that field in multipoles, and then if you integrate those tidal torques over the history, that's how you get how much torques, how much rotation does a proto-galaxy gain. But this is sort of the idea. Now, simulations show that a halo has a mean rotation, which is quantified by a dimensionless parameter like a lambda. So lambda is the ratio of the angular momentum of the halo, of the dark matter halo, divided by the angular momentum of the halo if it was just totally rotationally supported. Right? So basically, if the halo is rotationally supported, v squared by r equals gm by r squared. So that's like a disk, essentially, cold disk. So only it only has a 5% rotational support. That's like the typical number. So there's like a distribution of halo angular momentum. So galactic disks. So the question that we started with was how and why do some of the galaxies have disks? And the first part of that question I sort of motivated the answer to is that in the proto-galaxy stage, because of the quadrupolar distribution of mass around it, they get tidal torques which spin the halo as a whole. Okay, but the second part of that is some of this gas which is there in this proto-galaxy has to cool and lose its internal energy and collapse, and roughly conserve its momentum, so that all the random motion goes away and only rotational motion remains. Okay, so that sort of is the answer. So your disk galaxy has a sigma, right? Disks are exponential. This is equal to sigma naught e to the minus r by rd. The disk galaxies are exponentially distributed in terms of their mass. Let's assume isothermal dark matter halos. It's a good approximation. That gives you a flat rotation curve as well. So your rho as a function of r for the halo is equal to v200 squared by 4 pi g r squared, right? This is the density profile for a dark matter halo, isothermal sphere. density goes like 1 over r squared for an isothermal sphere, so that the m enclosed is proportional to r, and that gives rise to a flat rotation curve. Okay, so this is the isothermal dark matter halo. And this 200, if you remember, the halos have a density which just goes on forever. This R200 is the radius, which sort of defines the edge of the halo. Because outside that, the halo is still sort of collapsing. It has not virialized. R200 is the radius of, is nominal radius of a halo. It is the radius within which the mean density is 200 times the critical density of the universe. Okay, so m or m200 is equal to 4 pi by 3 r200 cube times 200 times 3h squared by 8 pi g. This is the critical density of the universe. This is 200 times the critical density of the universe. This is the volume of the halo. This is the mass of the halo, right? So this defines this R200. And V200, of course, is Gm by R200. Right, and there is T200. Basically, T200 is nothing but the dynamical time at R200. That's nothing but R200 by V200. So if we look at this expression, M is equal to 100 times R200 cube times h squared by g, right? This is what we have. So what this means is that T200 is equal to T Hubble by 10. This is a very useful relation. This is a very useful relation. So I just sort of cancel these factors. So 200, this gives 100. So T Hubble is equal to H inverse, right? This is sort of roughly the age of the universe at that redshift, whatever you're talking about. And T200 is just this. If we plug in this V200 there, and if we manipulate all this, this is what you get. What this means is that at any redshift, the dynamical time at the edge of the halo, is just 1/10 of the Hubble time. Very useful. Whatever halo mass you take, at the edge of the halo, the dynamical time is about 1/10 of the Hubble time. So the disk mass is equal to md times m. So this m is the halo mass, right? Most of the mass is in the dark matter halo. md is the mass fraction in the disk. Okay, so this is the mass in the disk, which is nothing but this, and that's nothing but md times v200 cube by 10 h z times g. I mean, you can write mass in terms of the radius, you can write mass in terms of velocity or T200. They're all like exchangeable. So you can actually write the disk mass as 9 times 10 to the 10 H inverse solar masses times MD by 0.05. So what I have written here is the mass fraction in the disk is 5% of the halo mass. 5% of the halo mass is in the disk. And that's a typical number. The disk mass for the Milky Way is about 5 times 10 to the 10 solar masses, and the halo mass for Milky Way is 10 to the 12 solar masses. So that's 0.05 is a typical number. It is somewhat related to it, but not directly. Lambda quantifies the rotation. This is just the mass. Okay. It's V200 by 200 kilometer per second. That's the rotation velocity of the Milky Way galaxy. Cube times 1 by EZ. If you recall, HZ equals H naught times EZ. This is how Hubble parameter is related to Hubble constant. This is just the solution of the background flat FRW. universe. Okay, so this is how the galaxy mass is. What about the galaxy angular momentum? JD equals 2 pi r, 0 to infinity r dr times r times sigma r, right? Uh, sorry, this is not JD, this is MD. This is the mass in the disk, right? So this is the disk mass is nothing but 2 pi r 2 pi r dr times sigma r. That's just the definitions. And sigma r we know is an exponential. If we put sigma r equals sigma naught e to the minus r by rd, we can actually integrate this. And this is nothing but 2 pi rd squared sigma naught. Similarly, JD is the angular momentum in the disk. That's 2 pi integral 0 to infinity dr r sigma r. That's just dm times v. The rotation curve in the isothermal halo is constant. So velocity is constant. It can be brought out of the integral. V times r. So V times r is the specific angular momentum. Specific angular momentum times dm, integrate it all over, you get the total angular momentum of the disk. That's equal to, if you plug in that exponential form, what you get is 2 times md times rd times v200. The local rotation is everywhere equal to v200. It's a flat rotation curve, isothermal halo. So this is JD. Now JD is equal to small JD times J halo, right? I mean, just like JD is the fraction of angular momentum in the disk relative to the halo, just like small md is the mass in the disk relative to the mass in the halo. And the spin parameter lambda is essentially J halo divided by square root of 2 mvr. So this is the definition of this lambda parameter that I mentioned. So if the halo was totally supported by angular momentum, lambda would be unity. Okay. And from virial theorem, we know that energy is equal to, or modulus of energy is equal to half m v200 squared. Right, so this is half, this is the kinetic energy. Basically, half m v200 squared is the kinetic energy. This is we are applying this to the whole halo. So this implies v200 is equal to twice e by m. So now we can actually substitute this v200 here in JD. So your RD is equal to lambda by square root of 2 gm by v200 squared JD by MD. This is nothing but R200, right? So GM by V 200 squared is just R200, right? R200 equals GM by, or V squared equals GM by R. This is nothing but V200 by 10 times Hz. Remember, the dynamical time at R200 is 1/10 of the Hubble time. That's just what I've written. Dynamical time is nothing but R200 by V200. That's 1/10 of the Hubble time. So this is that. This one, small JD by small MD. So small JD is the angular momentum in the disk divided by the angular momentum of the halo. Small MD is the mass in the disk divided by the total mass in the halo. So if we plug in the numbers, what we get is RD. So RD is equal to 7 H inverse KPC JD by MD lambda by 0.05 V200 by 200 kilometer per second, 1 by EZ. So you see, this gives you a roughly the correct scale of the disk, of the galactic disk for lambda of 0.05, right? Of course, if you put lambda of 1, you get a 20 times bigger answer, which is 150 kiloparsec, which is the size of the halo. Basically, what it means, if the angular momentum of the halo is huge, your disk will be huge. Okay. I'm assuming JD by MD to be the same, right? So the specific angular momentum of the disk is the same as specific angular momentum of the halo, right? So it's not as if the halo has given its angular momentum to the disk. So each component has about the same angular momentum per unit mass. So this sort of answers this question that we started: why are there disks and why are they rotating? There are disks because of this quadrupolar mass distribution, which talks the dark matter halos. The baryons in these dark matter halos can cool down and lose their thermal pressure, but they retain their angular momentum and they settle down in a disk, which is supported by centrifugal force, right? So Gm by R equals V200 square. So that sort of is the picture. Okay. So the key thing is lambda is about 0.05. That comes from a detailed calculation. And there is a spread of delta. It's not like all halos will have 5% rotational support. Some have 1%, some have 10%. It's some sort of a distribution, but this is the typical value. Okay, so we'll go back to the presentation. So now we are sort of changing gears a little bit. How do we find high redshift galaxies? It's very hard to find redshifts at galaxies at high redshift for several reasons, right? Remember, in the last class, we talked about this thing called luminosity distance and the angular diameter distance. Luminosity distance goes down rapidly as redshift, right? So luminosity distance equals 1 plus z times chi. If you remember your last class, the luminosity distance increases rapidly with redshift. The angular diameter distance goes like chi divided by 1 plus z. So the angular diameter distance is closer. So what it means is that if you take a galaxy and put it at a high redshift, its angular size will actually appear bigger compared to what if it appeared closer to you, but its luminosity will appear much dimmer. So let me just write down. dl is equal to chi times 1 plus z. Chi is this co-moving distance, and dA, the angular diameter distance, is equal to chi divided by 1 plus z. And for each cosmology, we know how chi varies with z. Okay, so what it means is that if you have a galaxy, okay, and if you put it at a high redshift, its angular size will be proportional to 1 plus z, and that's because of this, right? Right. So L, the actual size of the galaxy L, this is say L, is equal to dA times theta. Distance times theta is equal to the size of the object. So theta goes like 1 over dA, which is proportional to 1 plus z, whereas its flux will be proportional to 1 plus z squared, right? That comes from 1 over dl squared, or to the minus 2, right? On top of this 1 over chi squared, there is 1 plus z to the minus 2. So the area on the sky is theta a squared, which is 1 plus z squared. Area is angle squared. So surface brightness, which is flux by angle, which is proportional to flux by angle, will be proportional to 1 plus z to the 4. And this is actually a big problem. The higher redshift galaxies have an extremely small surface brightness. So it's very, very difficult uh, to be able to image them. If you put, say, redshift of 2, it becomes 3 to the power of 4. Right, so 3 to the power of 2, 3 to the power of 4 is 81, right? 3 is a 9, 3 is a 21, 81. So if you put a galaxy at redshift of 2, it becomes 81 times lower in surface brightness, and it becomes very difficult to observe it. So how do we go about observing high redshift galaxies? Uh, you cannot just blindly look at some region of the sky and say, oh, I'll be able to image a galaxy. You will need huge amount of time in order to do that, and that's not feasible. So what people have done is they have figured out some techniques to be able to detect high redshift galaxies. So here is the demonstration of one very popular technique, which increased the number of high redshift galaxies from 1 or 2 to thousands. It was a big breakthrough in 1990s, mid 1990s. And this technique is called the Lyman break technique. This sort of opened up the floodgates to high extragalactic, very high redshift uh, galaxies. Okay, before 1995, it was these radio galaxies, which were sort of looked at in optical and maybe confirmed. It was not a factory. It was not a big sample. This is the technique which allowed us to make big samples. So the technique is demonstrated here. So here in the solid line is like a model spectrum of a galaxy, of a star forming galaxy. And there are like features in this spectrum. So for example, here there is like a reduction of flux at this wavelength, right, at wavelength below 4000. This is actually corresponds to 912 angstrom in the galaxy frame. This is a galaxy at redshift of basically the Lyman continuum break. So below wavelength of 912 angstrom, all the gas, neutral gas in the ISM and the intervening gas in the IgM will absorb light emitted by the stars. So this is one feature. The other feature is, sometimes you have this Lyman alpha emission from the galaxies. If the galaxy is star forming, it can produce emission lines. Starburst galaxies can produce emission lines. So the idea behind this Lyman break technique is to design these filters. So here in dotted lines, you see some filters, photographic, uh, you know, uh, basically narrow band filters like U band, G band, and R band are shown. So at a redshift of about 3, if you see very low flux in the U band, but a reasonably high flux in G band and R band, that means it may be it's a good candidate for a redshift 3 galaxy. So here is the demonstration of this technique. Here is a patch in the sky, one of the small regions somewhere here in the big chunk in the universe. You see here, there's a galaxy in the red, there's a galaxy in the UV, in green, but there is no galaxy in UV. So essentially, this is UV, this is green, and this is in R. So this is something that this is the raw thing that you will see. That you don't see anything in UV, you see sort of a bright galaxy in green and red. That means it's a galaxy like this. And this may be a galaxy at redshift of 3 because of this specific feature in in the SED of a typical star-forming galaxy. So you see this. This is sort of the idea of this.
You're differentiating the galaxy from stars.
No, this is integrated light of all the stars. You remember in one of our very early lectures, I mentioned something about stellar population synthesis. That is, you take a standard evolution of stellar population with the IMF and so on, dust and whatnot, and you try to produce model SEDs for these galaxies. So this is a model SED.
So how is this method better than
uh, this is not the spectrum of this galaxy. This method is better than looking at so you need a very high resolution spectrum in order to produce in order to detect the SED of the galaxy. This is just broadband imaging. You just sort of image this galaxy in these three filters.
why not image it entire?
But that would take, like, hundreds of times longer time on the telescope.
Taking a single filter will take even more.
No. It's sort of, it's a broadband. You will have a lot of photons. It's like, when you want to do spectra, you have to split the photons across a lot of channels, and that, you don't have statistics in that. Doing spectroscopy is much more challenging than doing photometry. This is just taking images in these bands. These are the transmission functions of these bands. So this is the idea.
We don't put any filters, and we'll capture all the.
That's right.
So that would be better.
Right. So if you capture all the right, how can you distinguish this galaxy and this galaxy? You cannot, right? I mean, these are normal galaxies in the foreground. They are emitting in all bands. This break feature occurs at different wavelengths for galaxies at different redshifts. So if you choose a redshift, then you know how to choose your bands appropriately so that you have this dropout in the bluest band. But the galaxy appears in the two red bands. That sort of is the idea. Otherwise, the galaxies will appear bright in all the bands. So these are the galaxies uh, which are essentially all on this side. So in fact, if you do the same exercise for this big image, these blue circles are the ones which are candidate dropout galaxies. So their population is reasonably high. So once you have detected a plausible galaxy, then you do spectroscopy on this and then confirm that indeed this is a galaxy. And this is how you get galaxies at high redshifts. This is a very powerful technique. Essentially, this is the technique which has allowed JWST to see galaxies at redshift beyond 10. It's essentially the same idea. You are looking for these general features in the SED of galaxies, and you tune it to that particular redshift so that you see it. In fact, one of the big push for the infrared telescope is that all these features get redshifted to infrared if you go to redshift of 10, right? So this 912 angstrom if you put it at redshift of 10, it becomes 10,000 angstrom, which is like uh, uh, near IR, right? So there is near CAM. NIR CAM is one of the instruments on JWST, which is whose one of the tasks is to do this for much higher redshift. So once you have these candidate galaxy, you get time on 10-meter class telescope and just look at that galaxy spectrum and confirm it spectroscopically. But what this Lyman break technique does is it gives you a candidate which has a very good chance of success, unlike a blind survey where most of the galaxies are just not high redshift galaxies. Some starburst galaxies do show emission, but some don't. So there is a diversity of these SEDs, but some of these features are very generic. And that's what these selection of bands, that's what we are trying to accomplish by wise selection of these bands. So the top panel shows the U band dropout galaxy. It is clear. It is clearly detected in the two radar filters, but almost completely vanishes in the U filter. Bottom panel, in a single CCD frame, a large number of candidate Lyman break galaxies are found. They are marked with circles here. Their density is about 1 per arc minute squared. Okay, so this technique relies on our understanding of this stellar population synthesis, right? That there are these features in the SED of galaxies which we are trying to look for. So this is a plot of U minus G color, U band minus G band color versus G minus R color. So this is a color map for different types of galaxies. Like these are irregular galaxies, SC galaxies, SB elliptical galaxies. And this is evolution over redshift. So it's, so this is redshift of 3, and then this is how they evolve as a function of redshift in this color plot. Now at redshift of 3, between redshift of 2.8 and 3, essentially all these galaxies have the same location in the color map. What it means is that irrespective of the galaxy, whether it's elliptical or disk or irregular, they will have very similar appearance in this kind of a plot. Right? Their colors are essentially the same. So they will be dropping out in this band. So anyway, this is just the validation of this technique, right? This is a very, what do you say, empirical technique, based on stellar population synthesis, assumes IMF, dust, blah, blah. Lot of things go into it. So these have to be like verified and so on. These are some examples of 2 galaxies. So this is just stellar evolution shown for a bunch of different galaxies. These are 2 examples. So spectra of 2 galaxies of redshift about 3 detected by means of the U dropout technique. Below each spectrum, we show the spectrum of a nearby starburst galaxy NGC 4214 shifted to the corresponding redshift. It becomes apparent that the spectra of galaxies at redshift 3 are very similar to those of present-day star-forming galaxies. One of the 2 dropout galaxies features a strong Lyman alpha emission line. The other shows absorption at the respective wavelength. So let's see. This is that Lyman alpha drop feature that you expect to see in the U band. And then there are like different features. This is silicon 1260, 1303. I mean, there are a lot of emission and absorption lines. And this is the nearby galaxy. And you do see like there are matching features here and here. Like this is strong absorption in carbon 4 and emission in carbon 4. There is this absorption in Lyman alpha here. This is another galaxy. Again, it has, at the Lyman alpha location, it also has a narrow emission. You see this one? Sometimes, in addition to the absorption feature, you have emission of Lyman alpha. If it is a starburst galaxy, and if it lies in a region where it is not totally absorbed by the IGM, you can have this emission feature. So it's a messy technique, but our knowledge of star formation and galaxy formation is good enough that you can actually calibrate and fine-tune this technique. So now if you want to go to even higher redshifts, you use somewhat other criteria, but the idea is the same. Okay, so here there is a galaxy at redshift of 5.74, which is visible in the narrow band filter. In this filter, it's visible. You can actually see a smudge here, even here, but there's nothing here. Okay, so you don't see anything in R, V, and B filters, but in the infrared filters, you see something appearing. So that means the same feature which was appearing in the U band versus green and B band get shifted to infrared. See, this is, these are the background galaxies. This is that thing which drops out in R band and V band and B band. It's the same feature, the Lyman alpha absorption trough versus emission at higher lambdas. So it's sort of like this one. I mean, this is of course the usual technique that we've talked about. This gives no flux in U band, but flux in G and R band. So these different selections. So if you make these color plots and say, oh, if my galaxy lies here, this is what I'll call the Lyman break galaxy, or whatever Z break galaxy or whatever. and then that becomes a candidate sample to look using a follow-up spectroscopy. If you have a good number of photometric bands, then you can actually map out these different features in the SEDs, and then you have a better chance of your redshift identification being right. If you only have a small number of photometric bands, you don't get a good handle on the SED, different parts of the SED. So these are called photometric redshifts of galaxies, right? Based on these different cleverly selected bands, if you try to identify the redshift. Similarly, there's another feature in the SED of galaxies, which is shown here. This is the Balmer break in the rest frame of 4,000 at about 4,000 angstrom. This corresponds to the transition in hydrogen from n equal to 2 to n equal to infinity. N equal to 1 to infinity is 912 angstrom. N equal to 2 to infinity is 4,000 angstrom. So there's, in the SED of galaxies, you do see a sort of a jump even at this 4,000 angstrom. So you can also use that as a feature in your different bands to select dropout galaxies. So idea is actually important. We are not going into the details of the mess of how it actually works in reality. So here are some model stellar spectra. I mean, I've shown stellar spectra in past. So these are just pure stellar spectra, no dust absorption, nothing. Right? This is an M star, G star, A star, B star. And you see in the A star, there are a lot of Balmer lines, and then there is this 4,000 angstrom drop. In the B star, there is a drop at 900 angstrom, right? And that is what we are seeing in the galaxy spectra. Your sort of galaxy spectrum is an integrated spectrum over the IMF. So these features are there even in individual stellar spectra unaffected by the ISM. So these are spectra from a stellar population. This is from individual stars. This is if you take some typical IMF and some age and whatnot, and you see this 4,000 angstrom drop in the flux, very strong and definitive feature. And this drop at 900 angstrom is also very definitive. So these are the features that you are trying to infer from your cleverly chosen band. So this is a plot of the photometric redshift versus the spectroscopic redshift in something called the Hubble Deep Field North. Okay, these dots are all these galaxies, and you see that the photometric redshift is not so bad. It is more or less giving you roughly the correct redshift of the galaxy, and this is sort of the error in your redshift using the photometric technique. You're assuming that the spectroscopic redshift is the right answer, right? Spectroscopic redshift means that you have the full SED and you're just sort of mapping on top of a model SED and just reading off the redshift. So we see how accurate photometric redshifts can be. Their quality depends on the photometric accuracy in different filters, the number of filters used, the redshift and the type of galaxy, and also the details of applied analysis method. So there is a lot of mess behind this, in the sense of you also need this dust modeling, stellar population synthesis, IMF, and all that. But once you sort of calibrate all that, you get a decent sense of the redshift of the galaxies. So here is an example of different filters in this LSST. This LSST is like a big survey. It's like SDS, the successor of Sloan Digital Sky Survey. And what's shown here are these different bands. So this band, this band, this band, these bands. So the more the bands you have, a better handle you will have on the spectral SED features. And here in color are shown SEDs for different types of galaxies. And you can actually see this 4,000 angstrom Balmer break nicely. You see some emission lines and absorption lines, which are also very, very characteristic. So by measuring these features in your SED and by appropriately choosing a redshift, you can you can detect high redshift galaxies. LSST broadband filters UGRIZY. You see, they have increased the number of bands. And proposed narrowband filters, gray and rose shaded regions. So these are this is a broadband and these are narrow bands, for which many of the prominent spectral features have been labeled, except for the Lyman break, which is outside on the x-axis on the left, of course. This is only 300 nanometers. So that appears at 100, 912 angstrom, which is 100 nanometers. Okay. So this is like, really state of the art. This happens all the time. Even JWST uses the same ideas. And there are also other band selection techniques. This is like Z minus K color versus B minus Z color. And if your galaxy lies here, these are old galaxies at redshift greater than 1.4. These are star-forming galaxies at redshift greater than 1.4. So you do a photometric thing. You measure the colors of different galaxies. You put them there, and then you get these candidates, and then you follow them up. Okay, so you are trying to find the features in the broadband SED using your wisely chosen filters. Same thing here. So these are, this is in infrared. So this is J minus K color versus redshift for different types of stellar populations. This is like an old galaxy. Old galaxy is redder, and so on. So all this depends on the modeling, the type of galaxy. All these techniques also select certain kinds of galaxies. The galaxy selected from, say, the Lyman break technique is not a fair sample of the universe at that redshift. It only selects very blue galaxies. The reason being, it is very bright. It drops out in U band, but it is very bright in the G band. So that means it's sort of a blue galaxy. So it's sort of star-forming galaxies that you're selecting. Now there are things called deep fields, like Hubble deep field, ultra Hubble deep field, and whatnot. So these deep fields were small patches of the sky that these great telescopes like Hubble looked at for days. So this Hubble Deep Field North was something that Hubble just stared at for 10 days. Right? That's not an ordinary observation. You get like an hour, 2 hour maximum. For 10 days, you are getting to stare at one field. What that enables you is to be able to see very, very dim galaxies. You can actually go to very low surface brightness limits, and some of these galaxies are extremely dim. So you can do things like luminosity functions, right? Number of galaxies per magnitude versus magnitude. So this is the flux, basically, the apparent magnitude. This is dim, 30 is dim. So number of galaxies. Okay, galaxy counts from Hubble Deep Field and other surveys in 4 photometric bands, U, B, I, and K. Solid symbols are from HTF. Open symbols are from various ground-based telescopes. So these are from Hubble. These are from ground-based telescopes looking at the same region of the sky. The curves represent predictions from models in which the SED does not evolve. The counts lie significantly above these so-called no evolution models. You can actually see clearly the galaxy population must be evolving with redshift. The Hubble ultra deep field, this is the Hubble ultra deep field, is 3.4 arc minute by 3.4 arc minute, observed by the ACS camera. See, advanced camera for surveys. It's one of the instruments on Hubble. The limiting magnitude up to which sources are detected in this image is about 1 magnitude fainter than in Hubble deep field. More than 10,000 galaxies are visible in this image. Many of them are at redshift greater than 5. So this deep field is like a concept that's applied for all telescopes. All telescopes essentially look at these patches which are like, which are not contaminated a lot by our stars or our ISM, and you see it, and all the galaxies will see it. You can actually create samples of, for example, this is Chandra deep field from Chandra X-ray telescope, and you have these sources. So Chandra deep field south is an X-ray image of a 450 arc minute squared field, with a total exposure time of 4 million seconds. This is the deepest image ever taken in the X-ray sky. The right panel, this one, shows a color composite image taken with HST. So you then sort of correlate these, if the things that are bright in HST, are they also bright in Chandra? So this is like the survey mode. Survey mode is very essential for statistical studies and for finding like new things. This is JWST's deep field, the James Webb deep field. This is one of the 5 images that was released by JWST at the beginning. This is a galaxy cluster, and you can actually see the background lensed galaxies. The lensed galaxies, since they are magnified, one of the highest redshift, most of the very highest redshift galaxies are the lensed galaxies, because they have been magnified, and hence they are like easier to observe. So these are some more fields which are very popular in the sky. Cosmos field, ages, goods field, and whatnot. I mean, all telescopes stare at these fields, like, even UVIT on Astrosat, they will look at these, try to, make the UV luminosity function for the same galaxy region that Hubble has observed, JWST has observed, and then try to correlate them. This is an example of the same technique, the same Lyman break technique applied to some HST field at higher redshift. You see this Lyman break now is appearing at 1 micron instead of 0.1 micron. So this is like a redshift of 7, 8. Yeah, this is Z of 7 galaxy. These are upper limits in this band. These are observations in different bands in HST. And you see these upper limits. And this is the model SED. The solid line is the model SED that they find to be the best fit model. So the same technique. Similarly, you can actually see high redshift quasar. This is a redshift of 7 quasar. I had not shown a redshift 7 quasar earlier. You see here, the trough, the Gunn-Peterson trough is essentially complete. There is no emission. All that is noise. At redshift of 6 point something, we had some emission coming. Here, it's essentially 0. Now, this redshift of 7 is one of the highest redshift quasars. This is a quasar. You can actually see that this Lyman emission feature here. And the red shows essentially, if you don't have absorption, this is how the spectrum should look like. All this light has been absorbed by the neutral IGN. Now, these very high redshift quasars throw a puzzle. That is, how do you build such massive, a billion solar mass black hole so early in the universe? We have talked about this a little bit earlier. Again, this is sort of same stuff done in JWST. Let's see. The distant galaxy selected and confirmed by JWST JADE's program from the JWST near cam imaging at wavelength of 0.8 to 5 microns. These are different filters shown in the color mosaic. A is where A, B, C, D. Yeah, A is this thing. So galaxies with photometrically determined redshift estimates of redshift greater than 10 were selected for JWST spectroscopy follow-up. So here is that technique. Let's see. This is a redshift of 10, and you again sort of see this model SED and this break here. So your 912 angstrom gets redshifted to 1.7 micron. Same idea. Actually, in these 3 filters, you see 0. That is, in these 3 filters, let's see, where is the galaxy? Is this the galaxy? Yes. You look at this object, you see it here, 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 here. Not here, not here. So in these 3 bands, you don't see it. In the others, you see it. It's essentially the same idea applied to high redshift. So very, very powerful way of detecting highest redshift galaxies. There are things like starburst galaxies. So this is an optical image of a nearby starburst galaxy called antenna. This exquisite images you can only get from nearby galaxies. You cannot get this from high redshift galaxies. This is amazing. You can actually see individual star forming regions. So this is an optical image. This is an H alpha image. H alpha emission comes strongly from these Stromgren spheres. I mentioned to you about these things, ionized regions around star clusters. These are called Stromgren spheres, and they emit in H alpha. This is an optical image, plus superimposed on that, we have infrared contours at 15 microns. So this is dust emission, hot dust emission. What is this? This is an X-rays. This blue haze here is X-rays. So these starburst galaxies, merging galaxies, produce radiation in all wave bands. This is also in X-rays, and you can see these point sources. These are something called ultra-luminous X-ray sources, or ULXs. So they are associated with stellar mass black holes or neutron stars, which are accreting rapidly. So till now we were talking about optical and infrared, but you can also see galaxies in far infrared and in millimeter. So radiation in far infrared is because of dust. The stars make the dust hot, and this hot dust at hundreds of Kelvin emit in infrared. And this is a very characteristic spectral shape. So even here you can play the same games of trying to see these features in infrared and in millimeter. And here you also see emission from CO. These are CO lines, carbon monoxide lines, which are very commonly emitted by molecular clouds in the Milky Way, for example. Right, so this is just black body radiation from dust particles of different sizes. So you add the black bodies together, this is some sort of a thermal emission. And on top of that, you have these lines. So we'll actually not go, again, same tricks applied to millimeter and infrared. You can discover high redshift galaxies. We'll not go into details of this. These slides will be there. You can check these out. Again, just to sort of highlight this. So you see this point here at 500 micron, 350 micron, but you don't see it here at all. And that's sort of the same idea of the galaxy dropping out in a specific wave band, depending on this characteristic SED that you expect in millimeter and in infrared. So all that, once you have made the samples of the galaxy, how do you go to the physics? How do you go to the question like, how many stars, how many galaxies do I have within a certain mass window? How many? So these kind of things, like how does the luminosity function of galaxies evolve with redshift? Right. So that is the question that you are ultimately after. Once you've detected high redshift, that's very good. But how do you use it for science? The scientific questions, the physical questions are, what was the number density of the earliest galaxies? How did the number density of galaxies evolve with redshift? Is there a peak in the number density? Is there a peak in the star formation rate of the universe and things like that? So that after detecting these samples and using a stellar population synthesis, initial mass function, all those ideas, if you put together, this allows you. So you can actually measure these luminosity functions using different kinds of selection functions, like Lyman break galaxies or infrared galaxies, millimeter galaxies, and whatnot, and construct these IMFs, the mass functions of these populations at different redshifts. Once you have that, you are actually essentially after something like this. This is something called the stellar, star formation rate density, SFRD, star formation rate density as a function of redshift. And you can use different surveys, UV, H alpha, infrared, radio, in order to infer the uh, infer the luminosity function of galaxies. Okay, and you put them all together to infer how many uh, how much was the integrated star formation rate per megaparsec cube of the universe, per co-moving megaparsec cube of the universe as a function of redshift. If the star formation rate uh, in the universe was uniform, it did not evolve in the with redshift, it should have been flat. This graph should be flat. It's continuously forming stars, but it has a distinct peak here, and the present time. So this is called cosmic noon. Essentially, the star formation rate density was the highest at redshift close to 2. And now the star formation rate density has fallen down by almost an order of magnitude from cosmic noon. So this is cosmic dusk. So cosmic dawn is the first stars, which happens at redshift 2030. This is cosmic noon, and this is cosmic dawn, cosmic dusk. So this star formation history of the universe is inferred from techniques like this. And there are different proxies to get star formation rates based on infrared. The infrared is emitted by hot dust, but the dust is heated by star formation, young stars. So higher the number of young stars, more is the infrared emissivity. So they are proportional. You can infer star formation rate from your infrared luminosity. Similarly, you can use radio as a proxy for star formation, because this radio is coming from supernova remnants. The more stars you have, the more supernova remnants you will have, more radio emission they will produce. Similarly, H alpha is produced by these H2 regions. The higher the number of young stars, uh, bigger will be the H2 regions and higher will be the luminosity of H alpha. Similarly, UV and X-rays. So people have actually used these things to calibrate star formation rate from these observational proxies. And all that goes into making these. And then there is chemical evolution. So this is the part on stellar population synthesis, right? How is the luminosity of a population changing with dust? So metallicity should be evolved, right? The early galaxies did not have a lot of metals because they were not polluted by metals. The first stars were almost metal free, but they polluted the IgM and ISM with metals. And then the next generation stars had different metallicity. But the metallicity affects the evolution of stars in the HR diagram. Metallicity affects how much dust will be produced. So these theoretical models are extremely simple, but they have to evolve these metallicity and dust in the IgM and in stars. And that's what they do in the background in order to be able to produce this figure. Okay, so this is essentially a whirlwind tour of high redshift universe. Okay, very, very important topic at present in galaxies. I think this is the forefront of galaxies. It as exemplified by all these JW earliest galaxies detected by in the news. The new record holder for the highest farthest galaxy has been found, and almost every month you find some new news on this. So this is really the forefront. And I've only given like very ideas in a very coarse-grained way, but I think this is enough for you to latch onto some of these and read more. In fact, I would encourage you guys to pick up for your presentations at the end of this course, pick up one of these JWST papers or something which is really state of the art. It will be really fun to know about all this. Okay, with that, I'll end the class. So from next time, we'll do ISM. And I also have your papers. If someone did not check their marks, it's fine. Otherwise, I think all of you have